So just I recap the previous session. So what is the major evolution between the 5G to 6G? 5G actually in 2020 is already fixed in the 2 pvt. Maximum is given for each Mbps. That is a massive data rate. So right now it is converted for the 6G is a universal communication. And the second point is the ultra low latency in 5G. So it is converted for 6G is a hyper reliable low latency communication. And MMTC in 5G is currently in 6G. It will be the massive communication in 6G. So this will be held in 2030 is targeted for all the companies. So including these 3 points, already some points is extended for the 6G also. One is the ISAC, that is a integrated sensing communication, as well as AML. So morning session, one person is asked a question, where is the AML used? Yeah, exactly. So the AML is basically using in the physical layer and MAC layer mostly. So in physical layer, where it is using means, for example, actually what happened in the 5G general situation. So the base station will be communicated to the any user. Okay, through first initially sending some information. First we have to identify the user once. So once the user is identified, then it will be user will be sending some information to the G node. So G node be nothing but a base station. So what that information will be sending is that this channel RSRP, the signal to noise ratio. What is this from the, for example, base station here is there, some user here for here is there. So what are the information he will be sending through PRAS, that is called the PRAS, he said. So through that information will be sending. That information contains 3 parameters. One is the RSRP, and second one is the SINR, signal to interference noise ratio, and third one is the SNR, and antenna information also sending. So this is a data, very high data. So it take more time. So latency will be problem is coming from the 6G. So these will be decompressed. The data will be decompressed by using of some AML techniques. Okay, one more thing. So AML cannot be introduced anywhere because of it requires so much computing is required. Cloud computing is must be required. Because of we have to decoding anything is we have to some neural network, something networks is required. So cloud computing data will be taking more time for the decoding everything. So latency problem issues coming. So anywhere it cannot be defined by AML. So it will be applicable more for the physical layer or MAC layer. The MAC layer is for using for the scheduling purpose only. So this can be achieved in the physical layer. Some of the techniques is implemented in my PhD as well in the right now in the current company also. Introduce some of the techniques. Already I explained some RISAV, that is a reconfigurable intelligence services. The major target is that actually the signal to noise ratio enhancement. How to signal to noise ratio is enhanced was already discussed in the previous session. So I'm not discussing. The second point I will discuss, that is a low latency and massive connectivity. How will we achieve these 2 things in the 6G communication? So that case we are proposing one technique, that is a NOMA. Already everyone is knows NOMA, that is a non-orthogonal multiple axis. So first question you can ask, how will be used for the latency point of view? So what is the major definition of the NOMA is, so any information it can be transmitted in both the domain, in TDD domain and FDD domain. So there is any frequency, any time slot, it can be simultaneous transmission. There is no interference will be take place. So only it can be change the power coefficients. Okay, I will explain. That is a major thing in the NOMA concept. So, for example, if we can use the TDD domain, already everyone knows it. FDD and TDD domain, you can be transmitted any information. For the TDD domain, if you have some slot, you can allocate it. After the slot allocation, you can start the data transmission. It took time. Okay. For the computer 6G, the latency is less than 0.1 millisecond. So you achieve that target means that right now what is the NOMA techniques will be that is not sufficient. Okay, that's you have to go for the NOMA techniques. So NOMA what happened is it is not concerning. So it is TDD mode or time domain or anything, it is not matter. So it will be transmitted data. You can ask the one question, how will we transmit data without any interference? So that we have to explain here for the NOMA case. Yeah. So in this picture, we can clearly observe that the base station here is there, and 2 users will be there. One is a newer user, second one is a far user. So newer user having the channel gain is more than the far user gain. So here I am applying the superposition theorem at the base station. What is the superposition theorem means? Already you know in the signal system we got the subject also. So individual weight of the response system is equal to sum of the weight of the response system. So here base station I will transmit the 2 information. So what is the information of the near user information and far user information? So this is a superposition principle. H1 information near user, H2 information is a far user. With I'm assigning the two different powers. Okay, then power how can allocated means according to the channel gain. If near user having the high channel gain and far user having low channel gain. So high channel gain having I assign the low power. If you can low channel gain, I assign the high power. So see here clearly I write good sentence channel gains the H1 is greater than the H2, the power allocation is reversed. So PV is more than the P1. So what happened in the base station broadcasting the two user information with different power levels, and the receiver is receiving the two information. So this let us assume this is a S. So S information transmitted to the base station. The receiver using the receiving signal with channel is H1. So for example, near user received signal is Y1 is equal to H1 into S plus noise. Agree? So then how will be near user will be decoding the original information and how will be decoding the far user information. The near user you can apply the SIC technique, that is a successive interference cancellation. Okay, what is the meaning is that suppose you can observe in the block diagram. First I received that information superposed signal S. First initially what we did, so first you can decode the far user information. From the far user information is H1 into root over P2. This is the expected value of the second user, far user information. So after this decoding signal, so this decoding signal I will cancel in the So the far user information I subtracted from the original receiver signal. So receiver signal is consisting the S signal. So what I decoding the far user I subtracted. Just only have to receive only the near user information. This near user information directly decoding by using of the maximal activity function or match filter. You can apply anything of the decoding. Then you can get the original signal information. But coming to the far user, you need not record the any successive interference. Okay, you can decode the directly. You can ask the question why you can do the directly. So because of why you are doing the direct decoding, see, already channel is worst channel, H4. It is a very low value. Let us assume this very low value. I also assume power is a very low for the user one. Yes. So this is a act as a noise, N1. So it is a not dominated to the strong signal. So strong signal you have applied the high power and channel is worst, but it is a dominated. So you can directly decode it without interference will be happening, but some error will be coming definitely. But from these two concepts, the behavior is better than the near user and the far user. Okay. So I will show you this concept, the same concept in the simulation point of view. So how the behavior of the near user and far user, how the successive interference will take place. So let us see the MATLAB code. I'm running the code. See, so I'm not gone through this code completely. Just what are the concepts you explain? That same concept I will write in the. See, you can observe that. So near user give the better performance than the far user because of here I am applying the SSC successive interference. So far user getting the some bit that is higher than the near user. Okay. So two users he can be easily can upgrade. For example, I add the third user. Then what happens? Power will be distributed. P1, P2, P3. So then what happens? The three users performance will be degrading will be taking place. So no one is supported for the two users. Okay. For example, I wrote the code also for the three users. For example, I take the three users also. I will show you the code. So this is a code for the three users. I will run. So here one cluster I consider three users. One is near, mid, and third one is a far user. So change anything. So I wrote the code, same thing. I run the code. So see, here is this is better performance, but another two users will interference is happening. Is that clear? So what do you conclude from these two results, two MATLAB simulations? So it is very suitable for the users. If you can go to the higher users, then what happens? The interference will take place. So another drawback also will be there. If more than users will be there, more SSCs will be required. So it takes now more latency will problem arise. So then how can we mitigate this problem? So in my PhD, I did the one solution, I get this one solution. Okay. So this paper I published in the IEEE communication paper. So next paper, what is the concept is there? If more than users will be there, more than two users will be there, then performance cannot be degraded. For conventional normal, its performance will be degraded as you see exactly. But without interference, then how will the performance be improved by more than users, more than two users? That I will explain the concept. So this is a spatial modulation. I will explain later. So see here concept. So here I took down three users in this base station. One is from the near user. Means I can apply the SSC from the near users only. So I can apply the both the SSC. So what I did here is that first I took the two users, user one information, user two information, transmitted in the one time slot. Okay. Another thing is user 3 and user will be transmitted to another time slot. So here is I took the two time slots. One is event time slot and second one is a odd time slot. For example, in odd time slot, I am transmitting the user 1, user 3 information to the broadcaster from the base station. And event time slot, I am transmitting user 3 information and user 2 time. Okay. And another thing I also introduced in the system model, cooperative. So what is the meaning of the cooperative means? For example, you have the receiver signal. Once I decode it, I can forward to the others. So that is a cooperative nature. Okay. So I also introduced these things, cooperative nature. So I will consider in this system both the two users is act as a cooperative mode. Okay. So from this system model, from the base station, user 1 is receiving the signal from the event time, odd time. User 2 will be receiving the event time duration. For example, you can say only odd time duration. So odd time duration, what happens? User 1 and user 3 information received the receiver 1. Already you know the successive interference. First you can decode the R user information, that is the user 3 information you decoded. After that, user 1 information decoded. So while you are decoding the user 1, user 3 information, it will be the cooperative nature. It will be the forwarding to the user 2 and user 3. So user 3 will receive the user 3 information from the user 1. Okay? And similarly, from the receivers 2 also receiving the user 2 information and user 3. First will be decoding the user 2, user 3 information or user, then it will be the forward to the user 1 and user 3. So what is the final conclusion is that for odd time duration, user 1 will be receiving the user 1 information, user 3. So user 3 will be broadcasting user 1 meter. Why it is happening actually? No, it always in sleep mode, just you can sleep anyone here. Just see, just you can touch a black sleep mode. Touch sleep mode. What I'm doing actually. So user 1 will be receiving the user 2, user 3 information and user 1. In cooperative mode, user 3 information transmitted to the receiver 2 and receiver 3. So finally receiver will be receiving the event time, odd time, both time will be receiving the user 3 information. So from this system model, user 3 cell edge, the user 3 means this is the cell edge means it is a long distance of the base station. So it having the performance is enhanced. Okay. Simultaneously user 1 and user 2 also performance will be enhanced because of SACR implemented. Conclusion that in the previous case, if you using in conventional normal 3 users, some interference is common. But in this technique, so without interference, having a better performance of the solar. So let us next slide. Yeah. See, from this picture, I am increasing the antennas This is a transmit antenna. 4 into 2 meaning is NT is 4, receiver is 2. User 1. So this is a green line. This is a green line. So again I am increasing the user 1, 8 antennas into 2 receiver antenna. Then it is a, so from this figure you can observe that clearly. If NT will be increasing, the PF performance is gradually enhanced. That is already you know in basic thing. Okay. And similarly, user 3, you can observe that user 2, 4 and 8. If I am increasing the antenna, still it will be PF is not enhanced. Any question from this? Why it is not increasing? Here is increasing, but here is not increasing. Why? Because of user 3 act as a cooperative mode. Okay, it's receiving, just transmitting. No amplifying, nothing will be doing. So this is not impacted. So this is a performance is improved. So here I'm generally using modulation. It is the modulation I'm using for the user 1 and user 2. Go to the next slide. So the same model I will compare with the conventional normal. So definitely conventional normal give the better conventional normal. See conventional normal after the 24th, I think 25 onwards, the performance is a degrading conventional normal because of conventional normal is a power is a allocated 3 users and interference also forming. But our proposal model gives the better performance. So also compare with the conventional normal with 2 model system. With fixed of antenna 4 and 2. Next slide, please. Can you tell me what is the drawback of the previous system model? Our aim for the targeted to the 6G communication, not for the 5G. So in 6G you require the ultra latency. But latency, what happened here? Latency. For I am using the cooperative means latency will be increasing and decreasing. Increasing because of decoding and forwarding. It took time. Yes, but we have the problem is getting the latency problem is in previous model. So that can be enhanced by using a new model technique. So in the new model technique, same model. Okay, same concept. But only change is that I introduced the RIS. In the previous session, already I have explained what is RIS. And the RIS main motive is that enhance the signal to noise ratio with n times. For example, SNR is getting the 10 dB. Okay, I am using RIS n for n is 64. It's 64 times of the signal to noise ratio. And that I already explained in the slides, previous slides. So I'm not explaining right now. Just this model I will explain. Here also consider the 3 models. User 1, user 2, user 3. So user 1 I place in the cell edge. User 2 near to the base station. User 3 some far from the base station. So I sending the information through the RIS. So here information sending to the RIS. So can you go to the next slide? Yeah. So obviously already know the signal is passing through the RIS means if number of elements is increasing, then SNR will be increasing. SNR will be increasing means BR will be improved. For n is equal to the BR will be at the 10 dB, it getting some around the 10 power of minus 2. But increasing of n 8, 16, 32, 64, then will be the gradually is increasing. See n 64, then you get the BR around minus 15, you get the 10 power of minus 2. So everybody knows what is a BR. Can I explain? So BR is very simple logic. For example, I am transmitting 100 bits. Okay, you are receiving 99 bits. So 1 bit error. Then what much? How much BR? 10 power minus 1. If 1000 bits will be there, then 1 bit error, then 10 power minus 2. So this is a BR. So in wireless communication, you can measure 2 metrics. One is a BR, second one is a capacity. Capacity means some rate. Okay. These 2 parameters will be depending upon the SNR, signal to noise ratio. So signal to noise ratio. Okay. So signal to noise ratio, enhance will be, for example, already I discussed in the morning session, adaptive modulation. If I see, you can observe adaptive modulation. If SNR is better, then your data rate will be high. If SNR is bad, then downloading will take the more time. You can clearly observe that the concept is explained in the previous session, so I'm not taking before. So from this concept, why you are going to the previous model to this model means mostly focusing on the latency point of view. So here is the latency is increasing and decreasing. So because of your transmitted 3 users at a time, so there is no feedback and no cooperative. So enhancing the BR also. Okay. Next slide. Yeah, these will be compared with the conventional model. Okay. But you already knows everyone. If you publish the paper means you have to must be compared to some other results. That purpose I wrote all the things. Concept is same. Okay. So some reviewers will ask some questions. So you will be satisfied. So that purpose you have to give the result, but not important. Okay. Next slide. This is the same thing. This is for the non-user performance. So here you can observe from the figure. So ND will be increasing, then VA comes because of due to the only SLR. And then next slide. Yeah. See, this is a third system model. In this model, you can recap the previous model. I am not considered direct path. You can observe or not. So I consider only the signal will be transmitted through the RIS. So there is no direct path. Okay. So but in this model, consider the direct path. We can ask the question, why is the previous one you cannot consider, right now you are considering? Okay. The question is
hybrid
no. This is application for using for the device to device communication purpose. Okay, not for the machine to machine communication. In mind you have to doubt what is the machine to machine communication and what is the device to device communication. Anyone can answer this question. What is the device to device communication? What is the machine to machine communication? No, I will tell you. No problem. So machine to machine communication means, for example, okay, you can take up your printer. Okay, you say principal room. Okay, printer is an IT room. So, okay, principal wants the print. Then what to do? He went to the IT room? No, because of principal is very powerful. Then he can use a machine to machine communication. Okay, then he can press the button, print, then automatically it becomes. Then how will be happening? So first this information, whatever the print press button will be send some information to that machine. So that machine will be the print. So attender will bring that print. That's the concept. Machine to machine is it is mostly using for the vehicular communication purpose. Vehicle, for example, if you are designing any autonomous vehicle, okay, it will be traveling on road. Any obstacle will be there, obstacle in front of the vehicle. Then what to do? So it will sensing first. Then that information sent to the brakes, then brakes will be upright, the accelerator will be down. So these are the things will be happening. So it will be communicated as mission to mission inside. So 5G and 6G's main concept is the mission to mission communication. Actually 5G is not worked out still now. So every company is lose whatever the amount is invested in the 5G, that is not getting fulfilled. Okay, the 5G is ruled out right now in the industry point of view. So that's why more people are interested to do the 6G. So as well it maybe comes in the 2030 around. Okay. So that is a next topic. Okay. So this concept is applied for the device to device. So mission to mission is clear concept. So coming to device to device. So what is the meaning of the device to device coming to company means?
Device to device means within the area. For example, it's what you have on the lab. One phone to another phone. Right?
Yeah, that's partially is right. Partially right. But device to device communication means, for example, morning principal sir is worried about the hours, 8 hours. Okay, so signal is not getting proper in the room. Okay, tower is there here. Okay, tower is cost minimum is some billions money will be expended. So everyone is not built the towers. So what happened? Now to connect to the another device. That is a side link. In 5G terms is called side link in between. Side link means base station is there in the near the base station anywhere, but here signal is not getting properly. So we have to get some means in the easy words is the repeaters. Not exactly what that one. Repeater cannot be used. That is one device you can use. That device is a side link. But that device is not take much money. Okay, the device is consisting only partially, all the information not consisting. It only getting the signal and boosting and sending the surrounding areas. So that is a device to device. In 5G generally using the side links. That is called a side link transmission. So that is a device to device communication. Any question? No, thank you. So coming to the device to device communication point of view, the same technique I'm using, user 1, user, I took the 3 users. Actually, you have one doubt, definitely you will arise in mind. Sir, in world only 3 users will be there. So I always told the 3 users. Technically, not using the 3 users, 4 users. No one will ask a question. So, very simple. We take the one cluster. In communication, all of you know what is a cluster. Okay, in cluster, so if geographical area is there, we can divide in the number of clusters. I talk regarding one cluster. This is a one cluster. For one cluster, I can use 3 users. But according to the NOMA concept, you can use 2 users practically. But I propose this model, you can use 3 users. If you can have n number of clusters, then n into 3. So actually n into 2 is possible practically. But my research is doing the n into 3. So nobody will be there or not? Another question, you can ask the question. So the near user, you can use the SSC. SSC means far user information must be decoded. It means that near user having 2 information nodes. For example, near is me. So I information decode system. So it cannot be used for the NOMA is not used for the voice communication any other purpose. It using for the machine to machine communication or device to device communication. Not for the application for the practical applications. So practical application in 5G and 6G you can go. You must use the OFDM model. Orthogonal frequency division model. I will ask another question also. 5G NR is called, not 5G. So 2G, 3G, 4G is there, but 5G was certainly 5G NR is set. Why the reason is new radio means in 5G will be supporting the different number of subcarriers. Actually in LT will be supported only 15 kilohertz. 15 kilohertz will be supported. But going to the 5G, it will be supported 15 kilohertz, 30 kilohertz, 60 kilohertz, 240, 480 also. Okay. So you can ask another one more question. You can ask me a question. No problem. So why was that much of SES is required? Subcarrier spacing is required. Why? That is not sufficient. 15 kilohertz, 30 kilohertz is not sufficient. Yes or no? Why we are going to the 480? The answer is very simple. We are talking about the latency part. Okay. If frequency is increasing, what about the time domain? Decreases. So vice versa. So time domain is not decreasing. The frequency is increasing. Latency will be decreasing. So you can go for the 480. So that's why you have to go in the 5G. That is what we do. So that's what is given by the video. So it will be supported more number of subcarrier spaces. Okay. Next thing. Coming to the device to device communication. So in this model, I will explain to 3 different things. User 1, user 2, user 3, I am passing through the PD NOMA. So here title I am giving the hybrid NOMA. Is that clear? But first I will tell you what is hybrid NOMA. NOMA is okay. Hybrid is? Yes, definitely combination. OMA plus NOMA. Understand? OMA is orthogonal multiplex. So I will explain here. What is OMA? What is NOMA? Already well known, everyone is known capacity formula. C is equal to log of 1 plus SLR. The basic fundamental of the communication. Everyone knows. So this capacity can transmit it to the OMA, that is the orthogonal multiplexes or NOMA case. Is it clear? So, for example, I am getting 2 users. Okay. For the OMA case, what happened? The bandwidth will be divided. So total bandwidth is 10. Okay. For user 1, I allocated the 5 megahertz for the user 1 and 5 megahertz for the user 2. So for the C OMA, what happened? B1 log of 1 plus SNR plus B2 log of 1 plus SNR. Agree? This is the OMA. Is it clear? And coming to the NOMA, I told you latency point of view, same bandwidth. Okay, in same bandwidth, I am transmitting both the things. Clear? So B log of 1 plus SNR1, user 1 SNR plus log of 1 plus SNR2. This is SNR1, this is SNR. Agree? So comparing these 2 equations, this is better equation because of bandwidth is more. You can ask what is the effect of the bandwidth. Okay, how is it impacted the bandwidth in the real system? For example, I got the capacities of 2 bits per hertz. I got the capacities for the 2 bits per second per hertz. Clear? Here also I listen the 2 bits per hertz for normal case. Clear? So what is the bandwidth is, for example, you can took the 100 megahertz bandwidth. Total bandwidth is provided is given 100 megahertz. Then how much user 1, user 2 will be transmitted data rate? So this into this one. How much? 200 Mbps is transmitted. User 1, user 2 also transmitted 200 Mbps. Clear? But what about this case? This is a 2, this is also 2. But bandwidth is 50, this bandwidth is a 50. Then what happened? For one case, what happened? 100 Mbps, 100 Mbps. But here is a double. So that's why ROMA is helpful for the spectral efficiency also. Not for the latency, it is also helpful for the spectral efficiency. Okay? So same thing. I is called a hybrid ROMA case. This is hybrid. Means hybrid means I use the ROMA as well as OMA, both the combinations. Okay? So here is a three possibilities. This is a conventional ROMA, what we were discussing previously, with different power allocations, P1, P2, P3 with ROMA. That's the one case. Second case is first user and second user I use the ROMA, and third user I transmitted to the OMA. Means, see, you can clear observe. 2/3 of bandwidth are allocated for the user 1, user 2 with passing to the ROMA, and remaining bandwidth assigned to the user 2. And next concept is I create the user pairing. That is my proposal system model. So what I propose it is that user 1, user 2. Okay, that is the user pairing. Then I allocated bandwidth is half bandwidth, 1/2 bandwidth. And user 1 and user 3 allocated another half bandwidth. So how much user 1 we allocated bandwidth, total bandwidth? So listen, don't sleeping. This I know this is sleeping mode, everybody. Okay. Okay, be active. This is very interesting. So why these are things I'm telling that if you're doing any PhD, any concept, there is no concept. There is no technical concept. It is a linear algebra, mathematics, simple logic. Okay, just a very simple logics.
User pairing to optimize the power.
After this experiment, I'll tell you that. Okay. So user pairing is that. Wait, I stopped actually. What I question? Our proposal model. What is our proposal model? Is hybrid NOVA model. So user 1 and user 2 allocated the half bandwidth. That is the user pairing 1. Second user pairing 1. The next user pairing is user 1 and user 3 allocated another half bandwidth. Can you tell me how much occupied the bandwidth of user 1? Again, I am repeating. User 1, user 2. These two are the pairing. These two are pairing with bandwidth is B1. Okay? User 1, user 3. It is a pairing. Then I allocated bandwidth is B2. Total bandwidth is B1 plus B2. Then tell me what is the bandwidth of allocated for the user 1. Total bandwidth, very simple. Take a day. User 1 first time occupy avutundi, second time kuda occupy avutundi. Enta occupy avutundi? Half bandwidth. Okay, second time half bandwidth. So how much total bandwidth allocated for the user 1? User 2 how much bandwidth allocated? Only half of bandwidth allocated. So definitely according to the proposal model, so which one is better one? However, because of user 1 is getting the better performance according to the normal concept because of SSR using. So user 1 getting better performance. So user 1 is getting the full bandwidth allocation. Then total system what happened? Total system becomes right. So obviously coming to the result, I will take after showing the result. Next slide. See, this is sum rate. This is the capacity. So this is proposal system. That is means half bandwidth for the user pairing one, half bandwidth for the user pairing. So next is conventional hybrid NOMA and conventional NOMA. This is OMA case. So you can observe that dark blue line getting better capacity, getting around 20 sum rate at 30 dB. And the hybrid NOMA case, is getting nearly 15 dB, and conventional is getting around 10 dB. It gives better. Simple logic, but it was published in IEEE publication. It is impact at least 5. Okay, there is no logical thinking, no technical thinking. So only logical thinking. Then you are asked the question. Then how will be the user pairing and how can we allocate the power? Power allocation. Okay. You want to simulation wise or theoretical? Theoretical. Okay. See what happened in practically according to the path gain between the near user and far user. Okay. So according to the channel gain H1, H2, so power will be allocated. Okay. That the water filling concept, if you understand, I don't know. In wireless communication, is water filling concept will be there. You are taught the subject, they will understand. Okay, water filling means, for example, simple thing. నాలుగు బకెట్లు పెట్టా ఉంది అసలు ఓకే దానికి ఫుల్ వాటర్ సగం ఉంది ఇంకొక అలా తగ్గుతూ ఉంది ఓకే మీరు వాటర్ ఫిల్అప్ చేసినప్పుడు మీ ఆలోచన ఏంటి ఫస్ట్ ఏ ఫిల్అప్ చేస్తారు ఫుల్ ఉంది ఫిల్అప్ చేస్తారా ఎంటీ వన్ ఫిల్అప్ చేస్తారా ఎంటీ వన్ ఫిల్అప్ చేస్తారు సిమిలర్ వే ద ఛానల్ గెయిన్ తక్కువ ఏదైతే ఛానల్ గెయిన్ తక్కువ ఉందో దాని పవర్ ఎక్కువ ఎలివేట్ చేస్తారు దట్స్ అ కాన్సెప్ట్ అండర్స్టాండ్ సో you easily understand channel gain because of channel gain is easily calculated. Okay, in 5G it is very easy. 5G what happened now? How to channel gain will be calculated means 5G will be send some pilot sequence to the users. Pilot sequence means it is a QPSK sequence. Okay, you know everyone y is equal to hx plus n. Y is the received signal, h is a channel, x is a transmitted signal plus noise signal. X is a already know at receiver side. So you have to calculate the h. Y is equal to hx. X already tells you. Then I easily calculate h. So y is by x. Then you can calculate h. So once h can be calculated, then you can elaborate the power easily. So I know user one having the high power, so high channel gain. So I assign the low power. Okay. So user two having the low channel gain. Then I assign the low power. Simple. Okay. See, and this is a concept I am explaining. You can one more thing you can observe here, dotted lines is there. Okay, so dotted lines means while you are explaining in RAS concept, the phase concept I am explaining. The phase of 1 minute. Yeah, this one. This one. This is a total chain, total channel. Okay, so it can be maximized. This total chain, I am applying the Cauchy's inequality theorem. Everybody knows the complex number, Cauchy's inequality theorem. Then it can be right here. So when it will be maximized, it will be the 0. Sorry, this whole thing will be 0 or 2 pi. Then it will be the total channel will be maximized. So if you can maximize this, theta is equal to minus theta HL plus theta GL. Then this Z will be maximum plus n square. So in the previously, the n square will be getting only if you can. This is the phase is optimized properly. Then you can achieve the higher SNR. So see, for optimizing purpose, this is a without optimizing. This is optimizing. Dotted line indicator without optimizing. This is optimizing. I am using the HDFA. This will for the photo session. I think everybody is waiting for that question. Okay, no problem. First format is will be first.
Yeah. Not about vision. Yeah. Not about registration. Yes.
sum rate of proposed model. So our proposed model is given better performance. So next thing, I forcefully introduce a successive interference. So it is not possible in practical. Every time there is a successive interference, perfectly is occurred. Some error will be coming. So I introduce forcefully interference at the new reason. So zeta is equal to 0.01, 0.03, 0.5. So when the successive interference more, then performance will be degraded. But our proposed model is a hybrid normal C. For the interference added 0.01, then it achieved from 12 dB as a transmit power, it achieved the 8 bits per second per hertz. If you go into the higher end, then it is gradually decreasing. So it will be same affected for the other models also. So this is an indicator that success of parameter will be more and more, it will be affected the performance also as well as. Next slide. So this is already told that I use so many optimization technique, that is STR and alternate optimization technique. These two techniques give you the same constant value. It indicates that optimization is perfectly optimized. So who will tell you this optimization is perfectly properly or not? So using two other tools, one reference tool, what is our existing tool. So then you get it is properly optimized. So both will give the same result. So our proposal is properly optimized. So next slide. Yeah. So this is concept is different models. If number of reflective elements is increasing gradually from the 20 to 100, so gradually the performance also enhances all the models. So that is the RAS beauty. So RAS beauty is that if more number of elements will be there, it gives the more number of SNR. So it will be reflected both the sum rate as well as bit error rate performances. Next slide. Yeah. So still now we discussed that one is high data rate, second is the latency. For latency, you go for the normal. Okay. So next, 60 is required more tremendous high data. Okay. What are the 5G is there? That is a 10 times of the higher data is required. Why the data will be required means that is for the application for the virtual argument application. So many applications will be there. High video rate and 18K, 16K videos will be transmission will be taking place. That purpose is required the higher data rate. So if you want higher data rate means higher bandwidth will be required. For higher bandwidth required means you go for the higher frequency band. So that is frequency band is terahertz band. So the terahertz frequency is 0.1 terahertz to 100 terahertz. Okay, that is also using. Actually, if I see two bands will be there. One is FR1, second one is FR2. But in 6G also introduced FR3 also.
అక్కడే ఉండండి మళ్ళీ స్పీకర్ తీసుకుని వెళ్ళాలి ఏమనుక డ్రాప్ చేయాలి ఇప్పుడు పావు గంట అరగంట
సో terahertz what happens means terahertz channel will be having some properties means high power class will be there.
ఇక్కడ
high power class means for example TX in the RX will be there. Okay, it cannot be penetrated to the receiver side. So it is abstracted and it will be the non-items that will be existing in terahertz frequencies. So these can be mitigated by using of the IRS. So still now you use IRS, RS using for the only for the enhance the SNR. But IRS is also used for the enhancing the coverage area. Okay, that also will be so this problem model. See, this is the total distance between the base station to user P1 plus D1 and D2, D1 plus D2. I put the RS here in this middle of the position, middle of any one position. Let us assume this distance is D1, this is the distance from the RS to user is D2. Is okay? So total distance is D1 plus D2. So our aim is that we have to improve the performance, enhance the signal to noise ratio, SNR. Okay, next slide. See, in previous equations, we can observe it. G1 and G2 and e to the power of J beta is there. G1 is the channel between the transmitter to RIS. G2 is indicated to the RIS to user. But here one term is introduced, that is HL. Okay, this is a terahertz channel. This is indicator of power loss of the terahertz. Okay, and this is a theta definition. This is the RIS element representation. This is a channel model G1 and G2. Actually, I am not told that what channel are using generally. So generally using 2 or 3 channels will be there. One is a relay fading, resonant fading, and the Nagagami channel will be there. So So relay fading means it having both line of sight and non-line of sight. But result fading means only it having the line of sight part. For Terra's case, I use only line of sight part. Is that clear? So this is general mathematical equation for the result fading channel. Okay. So if k is equal to k1 is equal to 0, okay, in this equation G1 equation, so if k1 is equal to 0, then it becomes relay fading channel. If k is increasing, then line of sight path is increasing. Okay, that's the indication. Next slide. So this is I told the HL definition. Okay, this is a HL definition. This is a path loss. So it will be impacted on the. So these parameters is introduced. So this is a free space spending loss term, this term, and this is a molecular observation loss, this term. So actually the terra actually is some significant losses, path losses is there. It will be impacted by the spreading loss and molecular observation. For example, what are the water vapors if there in the air, that also impacted the path loss of the terra's frequency. So for example, for 1 kilometer you can consider, okay, water vapor will be there. It gives the 30 dB loss, path loss. That much of losses. So these all are you can mitigate it. Then you have to get in a better performance. So the question is that why that much of path loss will be there? Then why you are going to terrace means terrace providing the high bandwidth. So high bandwidth, high data rate will be possibilities there. So you have to mitigate the channel path loss. So mitigation of channel path loss and enhance the area coverages by using of IRS is possible. Okay. So these are the definitions indicate that path losses. Next one. So this is a SNR, is a basic SNR. Already I told that the SNR is maximum, the pi must be less within the 0 to 2 pi. It will be the maximum the signal to noise ratio. Optimizing second principle. Okay. This slide is very interesting. Is that? This is a distance. First I took the distance is 5 meter, means transmitter to the receiver. Black one. And distance is increasing. 30 and 50 meters. Total distance. This is the total distance. So in x-axis you can observe that this is a terahertz frequency from 300 gigahertz to 1000 gigahertz. Means it is a terahertz frequency. So this can be seen. This is a SNR. So particularly you can observe that for 5 kilometer distance. So for example, you can consider 400 meters. How much SNR will be coming? 20. Yes. For increasing distance 30, then it will be decreasing some low value, and also increasing distance, then it's nearly 0. Are you got it? So if distance is increasing, the path loss also increasing, the signal to noise ratio will be the decreasing. Is it clear? So then here something I noted this one. Okay, this point means this is without IRS, directly communicated. If I put the IRS in particular frequency, 400 frequency, so for number of elements I put the 16, then I get the how much NX is the SNR? 40 dB is NX. So this point is getting here. If N is 64, then NS is 17 dB. Then NS is 256, then 23 dB is NS. Means what is that meaning is that in terahertz also, if number of N elements is increasing, then signal to noise ratio will be increasing. If signal to noise ratio will be increasing, means performance automatically will be enhanced. So that purpose, in terahertz frequency also we can use the RIS. So this is indicated. So next is our signal is BF curves with optimized phase, without optimized phase. So N is increasing from the 16, 64, 128. The BF curve also performance increasing. Okay, next slide. Yeah. This slide is very beautiful, important also. What is this indication is that? Here is transmitter is there, here receiver is there. Okay. Then where you can put your RIS? That's the question. What did I get? So here is a transmitter is there, here receiver is there. RIS you can put the any between, anywhere. Okay. But anywhere means it will be affected the signal to noise ratio. Okay. So better position. What is optimized position? Where it is a give the better performance. So in this result will be indicate that see. That is the RIS position. You can observe that D1 is the distance between the transmitter to RIS. See, you can clearly observe that D1 is starting from the 0 to 50. Got it? If D1 is 0, it gives the better PER. Means RIS is near to the transmitter. So 0 to to 5, it is given better 10 power minus. Okay, so then the RI is moving away from the transmitter. Then what happens? BR is decreasing, means performance was decreasing. Again, next thing is BR moved to the receiver side. Then what happens? BR performance is getting. So what is your conclusion? Where you can put the optimized value of the performance? Where you can put the RIS? Near to the base station or near to the receiver? That's it. If you can put it in between, the performance will be the degraded. Got it again? So this is a deployment of your RIS position, where you can put the RIS position. Got it? So similarly, in the previous one, I will tell you one. This is summary performance. This is also summary performance is increased by optimized phase and without optimized phase. So with RIS, without RIS. So this black is indicated without RIS. Without RIS, it is worst performance. At 80 dB transmitter, it gave only 25 or 30. But
actually, sleep mode health is same.
next. So this is a key point for the garage frequency for increasing gain. The IRS is the best thing for the next generation of wireless communication. And from the above system also can analysis where the deployment of the RIS. So if you can put the RIS near to the base station or near to the receiver side, you get the better performance. And third point is you must be optimize your phase. If best optimize phase, then you get the better performance. The optimized position is coherent phase shifting technique. So it will be enhance the diversity gain also. Okay, so what is the conclusion is that the terrestrial frequencies and Roma, RIS, these all are the next generation wireless communication tools for achieving our targets. What are our targets? One is a massive data rate required, massive connectivity is required, low latency required. So these are the techniques, or these are the tools for the wireless communication. These are talking regarding only physical layer only. So in modem you have to design how many layers will be helping. So I am talking regarding only physical layer point of view. So I am research done in the only wireless physical layer. Okay, MAC layer also some enhancement is going on, and some other layers also going some enhancement is required. But you are achieving better performance. These are the techniques proposed for the next generation wireless, that for the 6. Okay. And next thing is next slide. These are the complications. Last slide. Okay. Thank you. So any questions? That's it. That's it. Yes, yes. What I understand from you. So one thing is enhancement. Yeah. Enhancement. For example, you are going for the garage. It is used for abstraction. Yeah. If you can go more abstraction with the part of becoming, there is a line of check converting to non-line of check. Yeah. Okay. But how will be the enhancing the properties? So still now I am discussing only single RIS. Okay. If I put the multiple RIS. No, very simple. Very simple. For example, this is a room is there. Okay. For example, we are applying the garage. Okay. I put the garage here. That one. Okay, and this one. Okay, then I stay here. I receive the signal or not? Definitely. How will we receive? I will put the constructive waveform. Okay, from here to reflected, and this is completely reflected. That RS is reflected to here. So then coverage will be enhanced. So you can put the multiple RS. Go for the multiple RS. Make the Wi-Fi. Yeah, everybody is using the Wi-Fi. Okay, so Wi-Fi को box system. Yeah, so Wi-Fi ఇక్కడ పెట్టుకుంటాం, వీటిలో పెట్టుకుంటాం. So everybody is facing this problem. one rule పెట్టుకుంటాం. So దీనిలో కలిసి Wi-Fi system ఖచ్చితంగా అవుతుంది కదా? ఖచ్చితంగా అవుతుంది. Yeah, okay. ఆ Wi-Fi connection ఎక్కడ వస్తుంది చూసాము ఇక్కడ. Some optical fibers is there. Yeah, so optical fiber is a core. So from one device to your device. Is it clear? From your device to, for example, you are put in one room, you are staying in another room, but you are not getting proper signal. Then RS is empty. Okay, then enhance. See, core, that is one example. If you went to the shopping mall, big shopping mall, so one thing you can observe that where the electromagnetic wave is propagated, where the electromagnetic wave is propagated, no, sorry, where there is a current will be passing, that places electromagnetic wave is not passing. That is the sense of electromagnetic waves, transmission line. If you put in your mobile phone, you keep in the water, you will not get the signal. Yeah, this is okay. But for example, okay, if you enter into the some shopping malls almost all are wood, constructed wood, some these all are non-electric conductor metal, non-conductor metal. So if there is a non-conductor metals will be there, the electromagnet is not penetrated. Okay, but your raw data will be coming up to your building. In the end, very simple logic. With cellular interconnector, small pillar, big shopping mall pillar, cellular interconnector, cellular fine, with white signal is coming well, very good. Mobile is coming. Now we enter the cellular signal. Then what to do? You can put another cover. Very high cost. Then you can put RS directly. Then the cellular will be coverage will be enhanced. Okay, what is the meaning is that core will be core. Cores are in touch. Core నుండి మన ఇంటర్నల్ గా ఏ ప్రాబ్లం వస్తుందో దానికి we can use the RS. ఇప్పుడు ఫర్ ఎగ్జాంపుల్ వైఫై ఉంది. వైఫై కేబుల్ తో వస్తుంది, ఆప్టికల్ కేబుల్ తో వస్తుంది. అక్కడ మీకు RS అవసరం లేదు. దట్స్ ద మైనర్ సైడ్. ఇది ఎక్కడ దూరం నుండి మీకు కోర్ డేటా వస్తుంది. బట్ మీరు ఇక్కడ నుండి వేరే రూమ్కి వెళ్ళాలి, లేకపోతే వేరే బిల్డింగ్ కావాలి. Then you can put RS. What is the data will be there in the same data will be getting the second room or third room, fourth room. So మళ్ళీ ఇంకో మీరు వైఫై రౌటర్ కొనుక్కోగలరు కదా. It is very easy. You first initial RS చెప్పినప్పుడు it is a passive element, passive reflective element. It is like a paper. Okay, big shopping mall వెళ్ళారు, just paper paste చేస్తారు. Okay, మీరు అంటే వైఫై డివైస్ ఎంత అవుతుంది, రౌటర్ కొనుక్కోవాలంటే again you have to spend some much money. So 2 routers, 4 routers is very costly. It is very cheap because of it is a very thick size and easily deployed. So that's why the RS may be useful. But we get the core power to in satellite also. We come in the satellite. Satellite how will be communicated? So one tower will transmit satellite and satellite to ground. Okay, our ground near area we can put RS, not in between. That's and another thing. For example, EAV communication. Okay. For example, here is the desert area. Imagine traveling area. You can put the one drone. You can place the RIS. It is covered with the RIS. The signal will penetrate and you can put the drone. So that purpose is the application point of view. It is not a core. This RIS is a passive element. It is consisting only pin layers, directed layers. It is only switching and on and off. That's it. It is not a big device. Controlling చేసి ఏదైతే ఇన్సిడెంట్ ఆఫ్ సిగ్నల్ ప్లాన్ రిఫ్లెక్ట్ సిగ్నల్ కరెక్ట్ డిజైన్ పొజిషన్ పంపించే RS. దట్స్ కంట్రోల్. దట్స్ అంతేగాని బేస్ స్టేషన్ మొత్తం రిప్లేస్ చేసి ద కోర్ నెట్వర్క్ ఇస్ కోర్ నెట్వర్క్. ఓకే, బట్ extension point. For ఇక్కడ అవుట్ పెట్టారు. దానికి for అవుట్ పెట్టిన 500 600 కాస్ట్. ఆ డోర్ దగ్గర some RS space చేశారు. That's the beauty of RS. That is not replacement of base station. Yeah. So I think in the next generation what happened, there is every mobile acts as a base station. మీకు తెలియదు మీ ఫోన్ will be sent the information to others. That's happening in the system. Because of there is not issue. 30 to 50, 100, maximum 100 for 50 meters systems. Okay, every device, so this main topic is power consumption is low. So మీకు తెలియదు మీ power drain అయిపోతుంది. మీ mobile drain అయిపోతుంది. These are things happening. So RX is we will solve this problem. That's a beauty. Maybe it is expected. So most of the companies doing the research, okay, the part2 vendors, so many companies. So one thing you have to remember everywhere, every wireless internet and different situations. Okay. So only is that Qualcomm and MediaTek one. These companies, but the wall company la RS deal చేస్తే ఖచ్చితంగా బయట మార్కెట్ వస్తుంది. వాళ్ళు చేయగలిగారని రాదు. छोटा मोटा कंपनी इंडिया में डील చేస్తుంది అది ఎప్పుడు రాదు. Definitely. Okay. ఎవరైతే మొత్తం పాపులేషన్ డామినేట్ చైనా కి డామినేట్ దుబాయ్ కంపెనీస్ ఆర్ డామినేట్. సో why will you develop any new technology? Take a patent in put in the 5 years 6 years. It is not necessary, but it must be used. You pay the money. That's it. It's a domination. That's a mafia. So no company is not developed in wireless communication. This is the reason. R&D may do something that is the logical also need to also. So unnecessary things only. Because mobile propose చేసింది అదందరూ పెట్టాల్సింది అది అవసరం లేదు. మీకు తెలుసు దీనికన్నా వేరే రిపోర్ట్ వాడితే బెటర్ పర్ఫార్మెన్స్ దట్ ఈస్ 3GPP. It's called 3GPP. Third generation partnership.